All right, in problem number 19 here in 2.1, they're telling you that the height in centimeters at a time t in seconds of a small mass oscillating at the end of a spring is given by this function here. So we've got ourselves, right, some kind of spring here and then some big mass at the end of it here. And now what's happening? We pull it down and then that spring makes it go back up and then down and then up and down, and it's oscillating, and the height is given to us by this function right here. So they're asking us two different questions here, actually three. They snuck a second one in here. In part A, they want us to calculate an average velocity on these two time intervals here. I'm not quite sure why. They started with a really small time interval and then went to a larger one. Now, as I've told you guys in class, you're going to be allowed to have that average velocity function programmed into your calculator, and you're going to be able to use that on quizzes and tests and all that fun stuff. So it's really not going to be necessary for you guys to show any work here. If we were, what we're doing here for average velocity is basically just the formula for slope. We're going to do this h of t function evaluated at 0.1, so h of 0.1 minus h evaluated at 0 then, all over the change in x, or really the change in t in this case, from 0.1 to 0 seconds. But once again, you guys don't really have to show all that work. You can go to your calculator and type that in for us. So I went over here onto my CAS, and there's my AV function already typed in, but I do need to define my height function. And in this problem, the book called it h of t, we've got it defined, though, as f, the way that we've put it in our function here, our calculator. So I am going to go to Actions here, and we are going to define this f of t function right here. So f of, and you can use whatever variable you want right here. I'll just go with x to keep it nice and simple, but remember guys, whatever variable you type in right there, that's the variable you have to use then on this next step. A lot of people get that wrong. So this function was 8 times the cosine of, in parentheses now, it was a 12 times pi times t. So 12, I got a pi here somewhere, there we go. And I can't put t now because I define this function as f of x, so I'll put an x there. Notice guys, way on the left-hand side of my screen here, there's an RAD. That's just an indication that my calculator is in radians now, which is what I want it to be anytime we're dealing with a trigonometric function. So I've got my f of x in there, right? And now I think I can go ahead and ask the calculator now to do a, wait a minute, I just realized a problem here. Where am I going to get to a V? All right, I got to go back to the keyboard then. That's a pain. Okay, so AV, okay, and now back to where we were. First on an interval here from 0 to 0.1. So that's all we have to type in. It'll take care of doing all the work for us, and we've got this answer here. We're going to round to 3 decimal places. I've got a negative 144.721. So there we go. And I want to remind you guys, the directions didn't say estimate here, it said calculate. This is the one and only correct answer to this question here. Now for the second one, average velocity from 3 to 3.5. Again, if you were showing your work, it would be h of 3.5 minus h of 3 all over 3.5 minus 3, but once more, that's really not necessary to show here. So probably the easiest thing for me to do now would be to go up twice, there we go, and then I'll just change the interval right here from, I believe it was 3, comma, until 3.5. So we'll hit enter right there, and we got 0 right there. And what that tells me then is that within this difference quotient that we had right here, the height at 3.5 and the height at 3 seconds must be the same. That's how we would get a 0 in the numerator divided by that 0.5 on the bottom, and we would end up then with 0. Now when we move on to part B, though, the directions change a little bit with an important word, estimate. It's instantaneous velocity at t equals 3. So that's why I wrote it out this way. The velocity at 3 would be approximately equal to, and now just trying to explain my reasoning, at this stage of the game, you guys, we are estimating an instantaneous rate of change by coming up with an average rate of change over a really tight interval. So I'm going to do basically the same thing I did here on A up above, the average velocity functions, but I want to choose an interval now that's really, really close on 3. So they didn't say to make a table. They didn't say to do this 3 times. They really just asked for one. I'm going to go with thousandths, everybody, with a symmetric difference quotient. 1,000th less than 3 seconds would be 2.999, and 1,000th more than 3 would be 3.001. And I think that one little calculation right there is going to get us a really good estimate now for what the actual velocity at 3 seconds is. So back to my calculator one more time. Let me do my average velocity function yet again, but let's change this interval now. 2.999 comma, and ending at 3.001, and that's going to get us a real good estimate for the instantaneous velocity at 3. 5 times 10 to the negative 10th. Okay, so anytime, hopefully you guys remember this from chemistry, maybe from physics as well, when you see scientific notation here, but with a negative exponent, that's your calculator saying that the answer there is really, really close to 0. Technically, that's a decimal point, 9 zeros, and then a 5 here. So when that happens, I feel pretty confident in saying that my answer here is going to be 0, because that's what it would be if we were to round that to 3 decimal places or not. I have a funny feeling that once we learned how to actually find instantaneous velocity in Chapter 3, we would find that the actual value there would be 0. But I don't want to get into that just yet. That'd be ruining all the fun of Chapter 3. Okay, so that's a wrap on number 19.